So imagine, if you can, an object that has the mass of our entire sun.
Okay.
Just take a second to really picture that scale. And now imagine taking all of that immense, unfathomable mass and just crushing it down,
Right.
relentlessly compressing it until it's roughly the size of a single city.
I mean, it completely strains the imagination. We're talking about a level of sheer density that, it completely defies our everyday understanding of how matter works.
Yeah.
Like, a single teaspoon of this material would weigh as much as Mount Everest.
A teaspoon. That
They
is
weren't-
just wow. And we aren't stopping there. Take that city-sized sun mass object and make it completely invisible.
Mm-mm.
No light, no ambient glow, just a dark, silent heavyweight floating out there in the freezing void of space.
It's terrifying, honestly.
Right. And now for the real kicker. Imagine that there might be hundreds of millions of these invisible objects just, lurking out there, scattered all across our own galaxy.
It feels like a premise ripped straight out of a science fiction novel, but it's actually one of the most pressing, tangible realities facing modern astronomy right now.
Which brings us to our mission for today's deep dive.
Well,
We are unpacking a super fascinating piece of research from May 15th, 2026.
yeah, the Science Daily article.
Exactly. A Science Daily article detailing a brand new study published in Astronomy and Astrophysics. And the whole thing really centers around NASA's upcoming Nancy Grace Roman Space Telescope.
Oh, the Roman Space Telescope is, it's going to represent this monumental leap forward in our observational toolkit.
Yeah.
What this research specifically highlights is a capability that could just entirely redefine our map of the Milky Way.
So we're going to explore how astronomers actually plan to pull off the impossible, right? Like weighing the completely invisible.
Exactly.
And we're also going to figure out what these hidden objects can tell us about the extreme outer limits of the universe. And, for you listening, I want you to think about how much we rely on our eyes to understand our environment.
Right, our vision is everything.
Right. Imagine trying to navigate and map out a bustling city, but like 90% of the skyscrapers, the cars, the people, they're completely invisible to you.
You'd have a wildly incomplete picture of reality.
Exactly. And that is the exact reality astronomers are facing with our galaxy right now.
Yeah, and to even begin piecing together that incomplete picture, we first need to establish what these massive invisible objects actually are,
Right.
and the mechanics behind why they've managed to stay hidden for so long.
So we're talking about neutron stars.
Mhm.
The article explains that neutron stars are these ultra-dense remnants left behind when massive stars explode. But what actually happens in that explosion to create something so dense? Like, how does that work?
Well, it all comes down to a catastrophic loss of balance.
Okay.
For millions of years, a star that's significantly more massive than our sun maintains this very delicate equilibrium. You have gravity constantly trying to crush the star inward,
Right. Gravity pulling down.
and nuclear fusion in the core
Yeah.
pushing outward. But eventually, the star runs out of fuel, the fusion stops, and that outward push just disappears.
So gravity just instantly wins the tug of war.
Instantly and violently, the core collapses inward under its own staggering weight.
Wow.
And the outer layers of the star, they sort of bounce off that collapsing core and blast outward in this spectacular supernova.
Right. The big explosion we always hear about.
Exactly. But that core just keeps collapsing. It gets crushed so violently that the basic building blocks of atoms, the protons and electrons, are literally forced to merge together to form neutrons.
Oh, wow.
Yeah. So that city-sized ball of pure compressed neutrons is what's left behind.
And according to the estimates in our sources, the Milky Way contains anywhere from tens of millions to hundreds of millions of these things.
Yeah.
Hundreds of millions. But we've only ever found a few thousand of them.
I know, the discrepancy between what theory tells us must exist and what we can actually see is just staggering.
Yeah.
Our models of stellar evolution over the billions of years the Milky Way has existed, they guarantee they're out there. They're just hiding in plain sight.
Because the few thousand we have found, they're mostly seen when they act as pulsars, right?
Right, exactly.
Like they're spinning rapidly, they're emitting these massive sweeping beams of radio waves or shining incredibly brightly in X-rays. They're making a ton of noise. But the vast majority of neutron stars aren't doing that. They're totally isolated, incredibly dim, and produce basically no detectable light whatsoever.
They're just drifting quietly in the dark.
Yep.
Sophia Kaczmarek from Heidelberg University, who actually led this study, she summarized the problem perfectly.
What did she say?
She pointed out, quote, "Most neutron stars are relatively dim and on their own. They are incredibly hard to spot without some sort of help."
Okay, let's unpack this.
Yeah.
Because searching for these isolated neutron stars is basically like trying to find a single burned-out firefly in a massive dark forest.
That is a great way to look at it.
You know it's in there somewhere, but because it isn't flashing its light anymore, your chances of actually spotting it by just, like, staring into the dark trees are essentially zero.
The burned out firefly is a fantastic visualization, and it raises an immediate question, right?
Yeah.
Why dedicate astronomical resources, time, money, a multi-billion-dollar space telescope to finding a dark firefly?
Yeah. I mean, if they're just floating out there acting as dead weight, what's the big deal? Why not focus on the stuff that's actively shining and doing things?
Because they aren't just dead weight. They're the key to unlocking how matter behaves under the most extreme conditions in the universe.
Right.
The pressures and densities inside a neutron star are so profound that they simply cannot be replicated in any laboratory on Earth.
Oh, sure. We can't just build one here.
Exactly. By studying them, we test the absolute limits of fundamental physics. Furthermore, we need to understand how the heavy elements, the building blocks of planets and ultimately biological life, how they're distributed throughout the cosmos after those supernovas. These stars are basically cosmic time capsules of extreme physics.
So if these stars are totally dark and we can't look for the firefly itself, we have to look for the dent it leaves in its environment.
Precisely.
We have to look at how its immense gravity alters the space around it, which brings us to the Roman Space Telescope and what it was specifically built to measure.
This is where observational astronomy gets incredibly elegant, I think. When you can't see the object, you look for its gravitational footprint.
And the phenomenon NASA is leaning on is called gravitational microlensing.
Yes.
According to the study, when a massive object, like our invisible neutron star, passes perfectly in front of a more distant background star, its gravity acts like a cosmic magnifying glass. It physically bends and magnifies that background star's light.
It's a direct application of Einstein's theory of general relativity.
Right?
Mass warps the fabric of space-time. Think of space-time like a stretched trampoline.
Okay.
And the neutron star is a heavy bowling ball sitting on it.
Oh, I like that.
Right. So it creates this deep dip. When light from a distant background star travels toward us and passes near that invisible neutron star, the light path is literally forced to curve around that gravitational dip.
The article actually makes a crucial distinction here between two different ways telescopes can look at this bent light. The first method is photometry. And photometry is basically just measuring the temporary increase in brightness.
Right, exactly.
A distant star suddenly looks way brighter for a little while because its light is being magnified by that invisible lens crossing in front of it. And plenty of telescopes can already do this.
Photometry is a fantastic tool. It effectively alerts us, sending a signal that something massive just crossed in front of this particular star.
Right.
But it has severe limitations. It gives us the silhouette, the shadow of the event, but it doesn't give us the exact weight of the object casting that shadow.
Oh, so we know something is there, but we don't know how heavy it is.
Exactly.
And that is Roman's real superpower. Because the Roman Space Telescope isn't just looking at the temporary flash of brightness. It's combining photometry with something called astrometry.
Yes, astrometry is the game changer here.
And astrometry is precisely measuring the tiny physical positional movement, like the actual shift of that background star in the sky.
And the scale of this positional shift is almost microscopic.
Really?
Oh, yeah. We're talking about tracking the apparent movement of a star that is thousands of light years away by a fraction of a single pixel on a highly advanced camera sensor.
That is insane.
It really is. And because neutron stars are so incredibly heavy, they warp space-time more drastically, creating a much stronger astrometric signal than smaller, lighter objects like, say, rogue planets wandering the galaxy.
Peter McGill from Lawrence Livermore National Laboratory, who co-authored the paper, he lays this out beautifully.
He really does.
He says, quote, "Photometry tells us that something passed in front of the star, but it's the amount the star's position shifts that tells us how massive that object is. By measuring that tiny deflection on the sky, we can directly weigh something that is otherwise unseen."
It's brilliant.
But wait, I want to pause on this because it's a bit of a mind bender. We aren't seeing the neutron star at all.
Not even a little bit.
We're purely looking at its gravitational fingerprint on starlight, way behind it. So if we just see a star's light bend, how do we definitively know the invisible thing doing the bending is a neutron star?
That's a great question.
Like, why couldn't it just be a really dark normal star or even a black hole?
What's fascinating here is that the astrometry itself provides the answer. Measuring the exact mass through that tiny positional deflection is what hands us the object's identity.
Oh, really?
Yeah. Up until now, our mass measurements of neutron stars have been incredibly biased. We've mostly been able to weigh them when they exist in binary systems.
Meaning they are actively orbiting another star.
Right. When two objects orbit each other, we can observe their gravitational dance and calculate their masses.
So historically, we had to rely on a buddy system. If a neutron star didn't have a dance partner to tug on, we basically couldn't figure out its mass.
We were largely blind to the solitary ones, but Roman's astrometric precision changes the game entirely. We can finally weigh the lone wanderers directly.
Okay.
Here is how the identification works. If the object causing the microlensing is completely dark, but the astrometric shift tells us it weighs roughly 1.5 times the mass of the sun.
Then we confidently know it's a neutron star.
Exactly. Conversely, if it weighs, say, 10 times the mass of the sun and emits no light, we are almost certainly looking at a black hole. The mass measurement is the definitive fingerprint.
So Roman finally gives us the technology to weigh these invisible ghosts. But what does that actually get us? Like, what long-standing cosmic mysteries is this new data going to solve?
Well, it's going to address some of the most fundamental gaps in our understanding of how stars live and die. Roman is preparing to execute something called the Galactic Bulge Time Domain Survey.
Let's quickly clarify that term for anyone who might not know. The galactic bulge sounds a bit funny,
It does sound a little weird.
but it's basically the densely packed downtown core of our Milky Way galaxy, right?
That's a perfect way to picture it. The center of our galaxy is incredibly crowded with billions of stars. Roman is going to repeatedly observe millions of those stars in that dense downtown area looking for those microlensing events.
Just staring at the crowd.
Right. By staring at a region with so many background stars, the statistical chances of catching an invisible object crossing in front of one skyrocket.
And the data from staring at that galactic downtown is going to tackle the mass gap.
Yes, the mass gap is huge.
The article mentions that right now, scientists honestly don't know the exact dividing line where a neutron star ends and a black hole begins. There's a theoretical boundary, but without enough actual data, it's just a blurry line.
It's a profound mystery in astrophysics. Theory dictates there is an absolute maximum mass a neutron star can support.
Okay.
If it gets too heavy, the structural integrity of those crushed neutrons fails, gravity wins the final battle, and the whole thing collapses into a black hole.
Right.
But observational data is so incredibly sparse, we don't know if there is a true empty gap in nature between the heaviest possible neutron stars and the lightest possible black holes.
Or if it's just a smooth, continuous spectrum.
Exactly. Roman's ability to weigh these isolated, invisible remnants will finally populate that missing data set and give us an answer.
The survey is also going to study something that absolutely blows my mind. The violent kicks neutron stars get from their supernova explosions.
Oh, the kicks are incredible. The birth of a neutron star is rarely a perfectly symmetric, gentle event.
Here's where it gets really interesting. When that massive star explodes, it doesn't always blast its outer layers away perfectly evenly in all directions, right?
Right, the explosion can be lopsided.
And when that happens, the core that's left behind the neutron star gets physically kicked by the asymmetrical force. Think of it like a cosmic billiards break.
I love that analogy.
You have an explosive impact that rockets this object across the galaxy. And remember, this object has the mass of the sun, but it's traveling at hundreds of miles per second.
It is essentially a sun-mass cannonball blasting through interstellar space. The sheer kinetic energy required to move an object that heavy that fast is difficult to even comprehend.
Hundreds of miles a second.
Yeah.
And because they are entirely invisible, they are just out there rocketing through the dark undetected.
Yep.
Sofia Kazmarek highlights why catching even a few of these speedsters is so vital for astronomy. She noted, quote, "We're seeing a small sample that's not representative of the big picture. Even a single mass measurement would be very powerful."
If we connect this to the bigger picture, mapping these kicks and understanding the true distribution of their masses will completely revolutionize our computer models of stellar explosions.
How so?
Well, currently, our simulations of how supernovas happen are based on fundamentally incomplete data. By finding these isolated high-speed remnants, we can actually reverse engineer the physics of the original explosion itself.
Oh, that makes sense.
And what's highly encouraging is the confidence coming from the Roman team. Peter McGill stated they aren't waiting around for years. Even in the very first months after the telescope is commissioned, they expect to start identifying promising microlensing events.
They are ready to hit the ground running.
Absolutely.
But, mapping these violent, lopsided supernovas, weighing hidden black holes, finding these missing millions of neutron stars, it's all revolutionary science.
Unbelievably so.
But the wildest part of this whole endeavor, based on the research, is that Roman wasn't even built to do this.
It's a brilliant example of scientific serendipity.
Yeah, the article highlights that Roman's survey was originally designed heavily around discovering exoplanets. It was supposed to use that photometric microlensing we talked about earlier.
Right, looking for tiny, temporary blips in a star's brightness.
To find planets orbiting other suns.
Which is a noble and massive scientific goal in its own right. Finding Earth-like planets is a top priority.
But its incredible astrometric precision, the ability to measure that minuscule positional shift in the sky down to a fraction of a pixel, ended up being an unexpected superpower.
It really did.
It threw the doors wide open to finding these hidden populations of rogue planets and, of course, these dead stellar remnants. Peter McGill says it plainly, this wasn't part of the original plan, so we can add a whole new kind of science to Roman surveys.
So what does this all mean? Like, how often does a tool designed for one specific task accidentally unlock a completely different area of discovery?
Oh, it's actually a hallmark of truly transformative observational tools.
Yeah.
When you build an instrument that pushes the boundaries of precision far beyond what came before, you inevitably see things you weren't looking for.
I love when this happens. It's a bit like setting up a highly sensitive microphone in the woods to record rare bird songs.
Okay. And then realizing your microphone is so incredibly precise, you're accidentally picking up the low-frequency rumble of minor tectonic fault lines shifting miles below the surface.
That's a perfect way to describe it.
You built the tool for the birds, but you accidentally unlocked geology.
Exactly. If the predictions in this study hold, Roman is going to deliver the very first large collection of isolated neutron stars detected purely through their gravitational effects.
Wow.
This demonstrates the immense value of adaptability in science. We engineer advanced technology to answer a specific set of questions, but the universe is vast and infinitely complex.
It really is.
The greatest value of these tools often lies in their ability to answer the profound questions we didn't even know we had the capacity to ask.
You set out to map the trees, and you end up mapping the fault lines beneath them.
Exactly. We set out to find planets, and we are going to map the underlying distribution of most extreme crushed matter in the galaxy.
So, to bring this all together for you listening, we have taken quite a journey today.
We really have.
We started with a galaxy hiding hundreds of millions of invisible, ultra-dense stars. We're now on the verge of launching a space telescope that is going to use an accidental superpower to track their gravitational fingerprints. Roman is going to physically weigh these hidden giants, mapping the lopsided aftermath of ancient, violent explosions, and perhaps finally answering where a dead star ends and a black hole begins.
It's a testament to human ingenuity. When we are faced with objects we cannot physically see, we learn to measure the shape of the space they disturb.
It's a great reminder that sometimes the most profound discoveries in life, or in the cosmos, are made not by looking directly at a thing, but by observing the subtle, undeniable impact it has on the environment around it.
Right.
The invisible always leaves a mark if you have the right tools to see the dent it makes.
The gravitational shadow is just as real and just as informative as the light.
And as we wrap up this deep dive, I want to leave you with a final, slightly eerie thought to mull over. We spent some time talking about those supernova kicks.
The cannonballs.
Exactly. The fact that the Milky Way is likely teeming with hundreds of millions of completely invisible city-sized objects, weighing more than the sun, rocketing through the darkness at hundreds of miles per second like massive cosmic cannonballs.
It's a lot to process.
It is. Given the sheer, incomprehensible scale of those numbers, what are the chances that one of these dark, silent heavyweights has already quietly passed right through our own cosmic neighborhood, completely undetected by us?
Oh, man.
Makes you look up at the empty, quiet spaces in the night sky a little differently, doesn't it? Just wondering what invisible, burned-out fireflies might be racing through the dark right above our heads.